It should be another draft physics video presentation. Draft science here on YouTube. Yay. Yeah. Anyway, uh, just doing this a different way using simple screen recorder, and the frame rate is terrible apparently. Not its fault. It's there just isn't any good webcam software for Linux. I mean, it just all sucks. But it does do things that are kind of cool. I mean, this is kind of cool. I have to admit, it's gimmicky and all that kind of crap, but I like it. So, just throwing it in there. But these are sort of some of the effects you can get, and that's kind of, I could just play with that all day. But anyway, to the video and such. So this is a Doc Schroeder, I think that's what it is, video. I thought they were a little seriouser than this. I mean, he's always trying to be humorous, I guess. But anyway, explaining the photoelectric effect, and they just say so many things that are just, they say them like they've proven them or somehow demonstrated it, and it's just all kind of just they're just talking like you would do at a bar or at the dinner table or something. What if? And they really haven't thought through all this stuff very deeply, and so I just wanted to get to some of those key points that are missing from anyone's description of any of this stuff. Frankly, it's all kind of weak and incomplete and insufficient, and I have to move this stupid lousy camera over, and then we'll do this thing. I suppose this should work. Well, good enough. So as I've pointed out, they want to turn something that has a frequency, all right, you can see that, right? Yeah. Into what they want to call a photon, and so they do some sort of thing and say this is a photon, and they know it has a frequency. They know that there's some idea that there's 500 nanometers or whatever of difference, in there somehow. Somehow it knows what kind of light it is, red or blue or green, but it's a blob, and that just doesn't make any sense. It's a frequency. It's it's stuff happening over a period of time that's decided by how fast it moves that little tiny distance at the speed of light. So how could you, if you're going to turn it into a particle, this isn't what you're going to do. I mean, obviously this is a photon in the sense that you need more than one of these to show up to know what frequency it is. You can't know the frequency unless there's more than one element to it. And so the logic would just say that yes, a photon is elements of quanta. So when Einstein said it's clumpy, or at least Feynman said it, the clumps would be inside the photon. I mean, it would be a clump, and then a clump, and then a clump. But see, they can't get past what Maxwell did to everything. This idea that it pushes and pulls, even though there's no evidence of that anywhere. There's only evidence of a push. Photons push things; they never pull something. But anyway. So I just, this is something they just never, and then you have to apply the other element that a photon has, which is polarization, and the polarization is proportional essentially to the wavelength. So you have to redraw this in some way where you have to account for the fact that these things, this arrival of the frequency arrives over a distance, and that distance is, could be, let's just say 500 atoms just for fun, okay, of distance. The photon does land on a rather large area. It doesn't interact with a single electron. There's no theory for that. So you have to kind of give the photon a shape, and that's only logical. So again, if you're going to do this dissection and explain why they believe what they believe, just notice, okay, that nowhere in their description do they talk about the elements, nor do they talk about this polarization in anything but a vague way. They don't ever mention that, well, the polarization is rather huge, in terms of the space it has to interact with. And how could something that's 500 atoms, across, or hitting 500 atoms worth of space, how could it affect a single electron? I mean, in theory, what I would say, if that's the quandary you had to solve, if somebody asked you, okay, solve that problem, how do I make something that's 500 atoms big interact with a single electron? Well, you could argue that, well, I could have one bit hit, and that could push, these electrons away, in the sense that it causes energy in this direction. Now the energy is reduced because it's going in more than one direction. So, like water, if I hit water, the wave I create isn't as intense as the energy that went in, because it's got to go in every direction. Energy going one way in has to be spread in all of these directions. So the energy going in these directions isn't nearly as strong as the energy that went in to make the droplet. If I drop a droplet, the droplet had more energy than the wave is going to have at any one location. You have to total the total energy over all this space to get back the original amount of energy. And the same is true here. And so the electrons, the atoms are all disturbed. And the idea is because of this polarization, so let's just say we cut this way down, just make it two elements, okay, with a distance between them. The idea would be as the first element comes in, it starts moving electrons at a specific speed dependent on the material, the substance, the atoms. And that's why some atoms reflect some light, and that's why they absorb different colors, is because that speed is different. And so the second one shows up, 500 nanometers later, let's say, of distance at the speed of light, and it shows up and it essentially gives a boost to that wave. That we caused the disturbance. The disturbance is being spread atom to atom, and now we're going to disturb it again behind, all right, that initial disturbance. So we're going to hit we caused the disturbance this way, and now we're going to hit again right behind that and cause that disturbance to be even stronger. And that's what causes the electron to be free. That causes the ionization if the frequency is high enough and the distance is short enough. Then you can understand that this energy boost, okay, is in a circumstance where it can free an electron, and that would be the photoelectric effect. So you're basically just saying that you gave the electron some momentum when you hit it the first time, but you're going to give it a lot more momentum when you hit it a second time, because it's already moving in the direction. So it already has momentum, and now you're going to hit it again and give it that extra amount that's going to make it possible for it to eject. Possible to not even eject, but just be in a condition where it's free enough that if you created a electrical potential, it could jump the potential. So that's pretty much the photoelectric effect. And the easier it's going to be to jump the potential, the further out, the more energy you can give it, the further away from the surface it can go, the easier it is for that potential to accelerate it. So what else do I need to say? So I'm just saying these are key things to understanding conceptually what a photon is, and there's just no denying it has to be stuff at elements of stuff. I mean, even if you have a wave theory, I don't think anyone's believing that one wave shows up at the shore and you go, oh, that's a 500 nanometer wave. I mean, obviously you could draw it, so you could say, okay, look, I drew it. So now I can tell that it's a 500 nanometer wave because I have one wave and I can measure it. But you kind of think, I think they would kind of know that photons don't work that way. That they're not going to be like an ocean wave, and you're going to, the surface is going to know exactly what this impulse was. But again, they've turned they've turned something that there's no evidence that any of this stuff is anything other than a binary signal. That is an on-off signal. It's that that's why they get the on-off pattern, is because it's an on-off signal. It's either on or it's off. There's either an element, a wave, or there's no wave. There's a wave, there's no wave. It's not doing any forward and back thing. It's just a very wrong notion. Yeah, this didn't do much. This isn't so much use. So anyway, all right. So this should work. Well, this should work, and it doesn't work. I should be able to shove that back over there. Leave the drawing there. Yeah, okay. So far, it's not terrible. I have to install the other. See, the problem is the camera software that really works. It screws up these stupid files, these stupid temp files, and it just starts eating your hard drive because it doesn't properly clean them. So you have to make sure they're cleaned before you reboot. I mean, every time you load, you have to make sure you destroy the files, and then you have to clean them up before you leave, or else the computer forgets and the space is gone. Little bugs, it's just irritating. But anyway. So far, I mean, look, I can't complain. The last month or so, Linux has been working fairly well. I mean, I did, the funny thing is, this Compiz, they call it, COMPIZ. Anyway, it's been around forever. I remember having a conversation about Linux like 15 years ago with a couple of locals, and, they were really enthusiastic. And they actually had it running then. Which is funny. This whole cube thing was working back then, but it just killed. It was just such a resource hog that it's all the computer could possibly do is that, and then it crashed. But anyway, and so it wasn't very impressive in a sense because it just showed that Linux was a gimmick. It really wasn't a viable alternative. But it is just interesting and I hate usually that kind of stuff. But I mean, I have to admit that once you start fiddling, with these, you start to say, oh yeah, I like that. I like this. I just like hitting the button. Oh yeah, look at that. I like that. All right. Anyway, I'm just. I usually don't go for that shit, but I'm going for it a little.
Bigger as the amplitude gets bigger. That's insane because these photons will be interacting with one electron and they will be sending their energy to one electron.
So this is the argument, right? Now they don't, they keep saying that, they keep Feynman diagrams, all that kind of stuff, but it clearly can't be one electron in any kind of rational sense. Now I would say it's one electron in the sense that you've taken, let's say the atoms are actually sharing the electron, or one's pushing the other guy out of the seat. Well, A guy hits into B guy's space, and then B guy jumps into C guy's space, and then C guy jumps into D guy's space. Obviously it's not the same electron anymore if I hit W guy and give him some extra velocity. So W electron wasn't the same as the first electron, the A electron that got hit the first time. So that's how I think they're messing this up. Okay, they're screwing it up. And they're clearly not understanding that if they understood the photon as elements, then they would understand that what they're seeing isn't wave interference. When they see the pattern getting broken of a photon, that all they're really doing is just reconstructing the photon, that they take the pieces and they break the photon and then they can remake it. It's a simple thing. It's just pieces. It's probably some way to analogize that to some Lego bricks, right? They're just 3 little Lego bricks or 2 little Lego bricks, and you can throw them in different directions and then reconnect them in some other location and make another photon. I mean, remake the photon you broke when you separated the 2 Legos. But that works. It works as a theory, and this doesn't, because again, he's not accounting for, you have this huge polarization of the photon. I mean, it's something they have to account for. They know it's there, it's real, and it has a real effect. So the part I didn't go over was the fact that the E equals HF, where they've converted frequency into an explicit statement regarding energy. So I guess I should just do a quickie on that. I mean, you people who've, you know, click faster, Darren. Anyway, no, I didn't clean the board. Ew. Well, we'll have to do it the old-fashioned way. All right, so, you know, it's so simple in terms of an idea, you know, that you can understand, you know, that if you have red light and then you have blue light, I mean, blue light is obviously in any period of time, you could understand you have more frequency, okay, more nodes to, if you have to insist on having a wave, you have more nodes to the wave, the higher the frequency. And so obviously these nodes, or what you're thinking are the bits that are causing the effect. They're the energy, you would say, right? I mean, if there was an energy to this item, this is it. But there's more to the story in the sense that it's not just the fact that the frequency is higher, it's also that the polarization is smaller, and that's something they never talk about. So because the polarization, or the you could argue the height, I suppose, you know, if you were to wave it. But the point is it's got this huge polarization, but the polarization for the blue light is much narrower, okay, than for the red. All right, the red is wide, the blue is small, which means the blue light hits a smaller surface, okay, it hits a smaller surface. Red light hits this big surface, okay, blue light hits this surface. All right, so that's also going to mean your energy is located on a smaller surface, and therefore has a higher potential, you could argue, whatever it's doing to do it. So clearly that's another factor, is that not only is the frequency higher, you have more nodes hitting a smaller amount of space. So obviously that implies, that's like taking the light bulb and turning it into a laser. Obviously it implies you're going to get more of an effect. Okay, the atoms here are going to be a lot more affected than atoms from the red light, just because the light is hitting a much broader area, the photon at the right frequency. So what else has to be said about that? So, and you know, and this is all premised on some notion that the conventional theory of light is that nobody knew the difference between, you know, infrared and ultraviolet. So you could argue that by the time of Maxwell, they'd already figured out some of this stuff, and that there's a difference in the intensity of light. But they say, well, the classical explanation is it's all the same. Well, I don't see anybody make that classical argument. So they're blaming history for not explicitly saying we weren't stupid enough to think all photons were the same. I mean, I don't even think Newton thought they were all the same. Yes, he put them in color categories, but you know, I have a notion in my head that he might have had some thought that, you know, there was a greater intensity to the stuff in the blue range than the stuff in the red range. But whatever. It's just sort of, it's such a cheat to say, oh, we had to make a new theory because the old theory was broken. There wasn't a theory. They didn't have enough information to have a theory. But I think if they were forced to speculate, they might very well speculate that, yes, it's a scale, and that the higher frequency, especially once they knew it was a frequency, would just overtly imply it, because you got more bullets. If I'm firing the gun a machine gun is, you know, more dangerous than a, you know, a hand pistol or something. I mean, obviously. And they just make this sound like, oh yeah, you know, classical physics made all kinds of assertions. They didn't make assertions. They just didn't know. And they're like saying, because they didn't know, they're saying, they're forcing classical physicists to assume things they didn't assume. I don't think Newton ever explicitly said, I'm certain that gravity is instantaneous. I mean, he just didn't know whether it had a speed or not. Anyway, continuing such.
And if you get more of them, that's what it means to get amplitude bigger, more photons will simply interact with more electrons, and you will get a greater current, but you won't have them going faster. Asterisk, how the heck do we tell how fast they are going? And I'd like to go into that by drawing this a little bit differently. Regard this battery. We're going to the next page.
Okay, so the diagram's sort of, it's just a photo multiplier type idea. A tube, photons hit one piece, they excite electrons, and then you have an electrical potential, and the electrons will jump the gap because of the electrical potential.
I'm going to draw a completely similar photoelectric effect setup, and I'll have the battery over here. We'll deal with that later. Here's the collector. Here's the emitter. We've got an ammeter here, and the battery is facing the wrong way. The battery says, no, don't bother coming over, electrons. I'm busy. So here is an electron, like here are these packets, these waves that are going this direction, but actually they're like wave packets. They are little bits, well, they're photons. Let's be honest with each other. I don't know.
Yeah, right. So let's be honest and say your description is mush, okay? Because you're not accounting for how big the photon is in terms of its polarization, nor are you accounting for the fact that its frequency, it just can't carry it the way you're arguing it's carrying it. It can't just say it can't have 500 nanometers written on it. It's just not going to work. It doesn't explain anything, and it makes all the theory kind of preposterous, because then you're stuck with this idea that a radio wave is sending blobs that are miles long. No, there's just a mile between the bits of energy.
What the heck that means, but they are particle wave things. They're little blobs of energy, and their energy is h times f. Turns out Einstein's right. So
again, I don't know why he's blaming Einstein for this one. I mean, that's Planck's thing. So and de Broglie. So yeah, I don't know why he's blaming Einstein for that one.
What they're doing is they're hitting this emitter, and then an electron is freed, and chances are that electron will go any which way. That's fine. It just got freed by the the photon. It becomes what we call a photoelectron, just because it's a regular electron that got freed by a photon. And that
right, so you're calling it something that is meaningless. It's a semi-free electron. It's an electron that has gained some distance from its connected proton, and therefore is in less gravity, you could argue. It's less connected. It's like Pluto. It's way out there, and if somebody else showed up with a little tiny bit of gravitational potential, it might decide to leave home for good.
If the electron is going the wrong way, it'll just go thump. Remember, check this out. This is going to be negative now, and this side is going to be positive. Sorry about my throat. Wow. Maybe I should eat more healthily before making these lectures. Then let's say this other photon comes in and hits this electron, and this electron just happens to be aimed exactly the right direction. It's like, bam! And this voltage here, between there and there, there's a voltage, yeah? It's the voltage between this plate and that plate. We could call that a stopping potential. In fact, that is what it's called. Stopping potential is the voltage between those two plates, and it says to this.
Right. So obviously you're not going to get too many electrons. The other way around, you get lots of electrons jumping the gap. You're not going to have too many jumping this gap. But the ones that do will be motivated. And the point is that they're going to have more velocity the higher the wave, the frequency of the light you hit. So if you hit with X-rays, then you get photons, you get electrons that are able to jump this gap with more regularity. And gamma rays, the higher the frequency, the more energy you have. And I would argue that just has to do with, you can sort of understand that as the energy of the first bit of the photon hits and it starts moving electrons, that movement isn't for free, okay, and it dissipates with distance. You could argue they're dragged, okay, to a halt eventually. And so the sooner you hit it, the more velocity you can add to it. So the sooner the second hit comes, the more velocity you're likely to add. Something like that could be an explanation. So I'll throw that in a draft category. That's just a draft statement, because it just might have to do with how many electrons you're disturbing. And the more electrons you disturb on the surface, the more likely it is that you've disturbed them more than once.
Electron, I don't want you to come over here. If you do successfully make it over there, then we will have a current. But there's no light coming on this part right here, so there's no way the electrons can come off of here and like do the effect backwards. So the only way we're going to get a current is if electrons do successfully A, get freed from the emitter, and B, happen to be pointing exactly the right direction, and C, be going fast enough so that their kinetic energy will transform into potential energy, and they will actually plump onto, is that a word? Yeah, onto this collector right here, and that will be...
Well, whatever. You haven't shown us these. You know, showed us the tube for the other experiment, but this one, reversing it, you know, you can't really guarantee that you don't have photons hitting the other thing and all of that kind of stuff. So, I haven't seen the actual experiment performed, so I can't say. It's not an incredible theory. All right, so I don't have any real argument with it, but I don't know whether, you know, they've interpreted so many experiments badly that, yeah, who knows? Yeah, it might be suspect.
A measurable current. You can imagine there's a stopping potential where I can stop everything. There's also a stopping potential where I get just a few of them through. And that's what I'm particularly interested in. The stopping potential where they only just barely make it. And that's what I'm talking about with K max. The maximum kinetic energy then must be the charge times the stopping potential. Q times V, because that must be the change in potential energy of these suckers to go from here to here. They're gaining potential energy to go to this negative spot where they don't want to be. But if some of them happen to be pointing exactly the right direction.
So the idea would be is that you set up the experiment and you start increasing the voltage against until you stop anything from happening, and then you'll know right at that point that that's how much your strongest electron, you know, the one that did make it before you turned it one notch higher, that'll just tell you what the maximum amount of velocity is for the electrons that are leaving. So you have to have enough velocity. Essentially, it's the opposite of a gravity argument, but it's the same argument in the sense that there's a force they have to overcome to be able to get to the other plate.
And given exactly the right amount of energy, then they will make it over there. That's how we can measure the maximum kinetic energy of these suckers. So here's my plan. I'm going to refute both the classical predictions and tell you what actually happened.
So there was no refuting of any classical prediction, because his classical predictions were entire straw men. So as soon as somebody had some notion that there was a frequency involved, they would be able to I'm sure people like, what's the guy who did the Hertz experiments? Not Voltar, but the other guy. Anyway, Ampere. Yeah, I think it was Ampere. No. Well, whatever. Hertz, maybe. Anyway, the point is, as soon as they knew there were all these frequencies, I'm sure they were pretty darn sure that the radio frequencies were a lot more benign than, say, you know, the light and beyond. So to say that the classical physics had no clue and that they asserted that all photons were alike is just a lie.
And then we'll see how quantum can explain it. This is the real result of this experiment. First of all, the light has to be the right color to eject electrons. You do not get any electrons
It doesn't have to be. So the point is it all it has to do is be above a threshold. So they keep talking about this like it's ultraviolet light or something, or just a specific kind of light or a specific color of light. Now, any frequency that's smaller is going to kind of guarantee that you're putting more energy in, and therefore you're going to move the electron out further. So anything higher than blue would cause the effect. And the higher you go, the more of the effect you'll see. So, they sort of, they imply otherwise, which is just wrong.
out, even with no stopping potential. You don't get any
So the whole point I would argue is I could make the argument that polarization is controlling it entirely. So as you narrow the polarization, that is, you make the light hit a smaller and smaller surface, the photon is hitting a smaller and smaller surface, you narrow the energy to a smaller and smaller piece of space that it's going to land on, that could be the obvious explanation.
electrons out unless the light is the right color. In fact, there is a cutoff frequency, and color is correlated with frequency, of course, so that means there must be a cutoff energy. That energy is a very interesting energy. So let me first say cutoff frequency, and I'll call that F naught. That is the maximum, the minimum.
So it really just depends on what kind of material you're hitting. So if you're hitting tungsten or some other kind of metals, you can actually create X-rays with, ultraviolet light.
Frequency you have to free these suckers. What I mean is it's the minimum energy that you need to have. We could put little knots on here, the cutoff frequency and the cutoff energy. Cutoff frequency or higher needed to get any.
So I think you could just rephrase this as the ionization energy, because you're basically ionizing the atoms, right? They're losing electrons there. Obviously, you're creating ions. So it's basically saying at what level do you start to ionize the atoms? That is, break the electrons, give them enough energy to leave their atoms.
Current. Whoa, that is incredibly profound. They're saying regardless of how bright the light is, if I come in there with these different colors of photons, and I'm sending in a red photon, for instance, it may not emit any electrons at all. And
so they've sort of changed this story over the last 5 or 10 years, where they've done some experiments where they hit it with a lot of infrared radiation, a lot of heat, or a lot of red light, and they can cause some electrons to leave. So it's not exactly true. And I would argue that that's probably because photons are hitting in exactly the same space. So the more you throw, there's more chance that you might end up with two red photons that actually are hitting the same area and they're perfectly out of phase, which would mean they create a blue photon.
And then I switched to pink.
Yeah, it's theoretically possible.
Well, I don't even know what that's doing in there. I switched to orange, it doesn't emit any, and suddenly at yellow it emits some. And the interesting thing is at yellow it emits exactly the same number as at blue for the same brightness of light. Oh, that's really interesting. And purple also lets the same number of electrons out. So there's you gotta be at least this high energy in order to free something. That's like having just enough money to get your uncle.
So the problem with these kind of analyses is that the range of ultraviolet is huge. It's bigger than the whole range of visible light. All the visible light's a tiny range, and then you have a huge category of ultraviolet and then another huge category of X-ray. So that's more of a category issue.
Out of jail. This is related to the fact that these electrons are bound in here, and if you don't hit them hard enough, they cannot get free.
Right, and this whole theory of hitting electrons, right? That's another point that just, it's not talked about much, but I mean, their model of the atom, where you have this tiny, infinitesimally small nucleus, and then you have this infinitesimally small electron, miles and miles away. It just doesn't make any sense that anything gets hit. So clearly I think, the truth is that the electron has to be in size, not volume, not density, but in size, bigger than what they're describing, because how the hell could it ever collect a photon? How could it collect any energy? I mean, it's got to have a surface because it can't attract photons. You know, there's no charge on photons. It can't just say, you know, bend to me. It has to actually hit it, and it's got to hit it, you know, with an element that's really tiny. The elements of the photon are really small, the little bits that make it up, but the photon's very big.
It's a wonderful video that says that there's a pit and the electron is a ball in that pit, and
right. So I mean, this is a nice analogy, but it's, you know, it really isn't a very good, because you should be able to describe it using the real mechanics, and you could just sit there and say, look, I have a couple of magnets in a condition, you know, where they're attracted to each other, all right, but there's other magnets that are repelling them, so they're in a balanced condition, and you can sort of do that with magnets on a stick. You can have them levitate and balance against a force, so you can understand they could be in a balanced state, and what you're trying to do is, you know, you can wobble the magnets and feel the tension that's holding them together, and there's a certain point where, wow, there's just no energy. You know, I go a certain bit away and there's nothing. I don't feel a thing. So it's free, and it takes a certain amount of energy to kick it out where it doesn't go back again. See, if I pull a little bit uneven, I go a little bit uneven, it wants to keep going back to the center. You know, I can push it off, but it's going to keep trying to get back to that center. And so that's just the tipping point argument. You can need enough energy, you got to get it going in the right direction and hit it again to free it. But once it's out here, I mean, it is so free. You know. And that's probably another reason why you can do this electron kicking thing, is because it is magnetism, and magnetism is the R-cubed rule. You know, it degrades with distance much quicker than just charge. But anyway, leave us continue.
if you hit that ball, then it can make it out. If you don't hit it hard enough, it'll just go whoop up the edge a little bit and roll back down. The electron will remain.
So this doesn't really even explain the difference between red and blue, because it doesn't really explain that the reason why the ball is going to pop out of there isn't because you hit it once. It's because you hit it with a frequency, all right, and you popped it out because you had it going, and then you pushed it again harder, and that's what freed it. So it's more like the argument is that you gave it momentum and then you gave it more momentum. So to make that drawing make sense, you could say it was stuff that had to hit it, rolling behind it. So it pushes it halfway up, and then another bit pushes it the rest of the way up the hill. But if it lets it swing back down to the bottom, then it can't hit it out. The second bit comes too late, it won't be able to roll it out. So if I'm rolling little balls behind that one that's stuck in there, you can understand that if one hits it right at the bottom and pushes it up the side a little bit, and then another one comes quickly enough and hits it again, it can get it out of the hole. But if it shows up too late, then the ball rolls back down and you can't kick it out. So, but this analogy is just so distant from what an atom actually is that why don't they just use the real example that we already know that electrons are held in a kind of gravity, so to speak, a force holds them in positions, and that you have to hit them before they move back into their position. So you hit them once, they move out of their position, and you got to hit them again to move them out of the atom. And I would just argue that polarization is telling us it doesn't happen to one electron. It happens to an electron. That electron's movement is transferred to other electrons, and then some other electron gets that second hit that liberates it. That's the sensible description that actually works, that doesn't have a whole bunch of, well, what abouts, and what about. This is full of, well, that's not even a right analogy. You're not even on the right subject.
Trapped. But if you hit that sucker hard enough, it can go bam, and it will be free.
So again, he's saying that somehow the ultraviolet light hits harder. No, it hits with the right frequency. And the right frequency basically is, look, it's a pendulum, okay? And we're not letting the pendulum swing back and forth. We're really just talking about the motion in one direction. So you know, if you have your pendulum still and you poke it in that direction, you kind of know that if you wait for it to start heading back down, right, that it at the base it's going to have its maximum acceleration against you. So if you wait till then to hit it, you have no chance of going up higher. Now, if you hit it when it's here or here, you know, somewhere else in the arc, then you have some chance of hitting it higher than it's the position it was at before. So you have to hit it before its momentum in the opposite direction is more than your momentum opposing it. But in theory, what you really want to do is hit it while it's still moving. While it's still going in the right direction, you want to hit it again and then add the energy, because that'll be all added energy. If it doesn't have any energy against you, then all the energy you put in will be with you, and you'll end up making the pendulum swing much further. That simple analogy explains so much deeper and better than this. It hits it hard enough. No, it's not about how hard it hits. It's about what timing it hits at. And again, this is just yeah. I mean, this is something everybody's got to know. You know, you can, tipping point. I mean, that's how they say Easter Island. You know, that's how they move those big giant rocks. Is they just tied strings on them. You know, and they just wobbled it by tipping it. You know, putting it on its edge, moving it edge to edge to edge to edge, adding energy.
And its maximum kinetic energy is given, well, we'll see a cool equation for the maximum kinetic energy. But I want you to understand that color of light, some colors emit electrons and others don't. And it also depends on what...
So again, it's really out of any range of visible light and colors. So color is kind of it's not really being fair to colorize all the other radiation.
Material we've made this emitter out of. Whoa, that's kind of funky. All right, so let's check for number 2. Just to re-emphasize number 1, brightness doesn't matter. It is only frequency. Whoa, that flies in the face of all classical physics, because brightness...
So, of course it doesn't, okay? Classical physics knew what tipping points were. Okay, classical physics knew that if you want to knock something over, you got to throw your rocks at the right frequency. So again, this is nothing to do with, oh, we had to find all brand new physics. No. Classical physicists weren't as stupid as these arrogant, obnoxious cartoon characters make them out to be. They were pretty smart people, and they made honest and decent mistakes rather than your arrogant kind of mistakes. You know, they didn't go around saying, oh yeah, well, it's this thing. It's a roundy thingy with a wibble in it. They didn't have any theories like that, frankly. And whatever ones they did have like that, they didn't publish them. Okay, they didn't publish them as, oh, this is my attempt. No, they either got it right or they kind of said, well, we'll wait till we finish it. We'll wait till we have an idea that actually works. You know, one that accounts for polarization and all these other elements that we know exist. Oh, I just, you know, I really find this irritating that they do this obnoxious pretense that, you know, they've advanced physics because they figured something out when they're forgetting what a tipping point is. So classical physics was at least smart enough to know what tipping points were and know that hitting something with at its resonant frequency means you can add energy to a system. And hitting it opposed to that means you'll not add energy.
Is amplitude. See the amplitude right there? Brightness is amplitude in classical physics. And if we... So
again, more, you know, there's no reason to think they didn't understand that you can have more or less photons. And that's what they were talking about. They didn't think that the little element of the photon got stronger or less strong or some other kind of thing. So again, they're just putting words that don't belong in classical physics mouth.
Talk about particles of light, we have quantized them, we're doing quantum physics, then we say that brightness is quantity. It's a whole bunch of photons rather than a whole big intensity of light, meaning big amp.
So that didn't sound very well. A whole big intensity and amplitude versus blah blah blah, some ambiguous notion of frequency. So again, it's all depends on the system you're hitting. So again, this isn't about the photon, it's about the system the photon is interacting with. That's what will decide whether something gets tipped over. So you don't be fooled. This isn't about adding energy. The red light adds plenty of energy. It heats the metal, it heats everything up, it does lots of stuff. So don't pretend it isn't adding energy. It doesn't have plenty of energy. So it's not about some explicit amount of energy. It's about the fact that every substance has a vulnerability. It's like water molecules and microwaves. We wouldn't have microwave ovens if it wasn't for water molecules being particularly sensitive to them. They like to vibrate at the frequency of microwaves.
Amplitude of the wave. The second observable fact in the photoelectric fact, and we can literally do this in an AP physics lab, ain't no thing. The second observable fact is that if the frequency is greater than the cutoff frequency, increasing the intensity, like what I mean is we have enough energy to free these suckers. If we've got at least this much energy, so I'm going to say if energy of the light is greater.
Obviously, if you're firing the bullets at the right frequency to tip over something, you can, if you fire more bullets at more things, you'll be able to tip over a lot more things. So, yeah.
Than the cutoff energy of the light, or, oh, sorry, the parentheses should start there, or F is greater than F naught, increasing intensity increases number of electrons.
Yeah, so again, it just, once you have the right frequency, then you can affect lots of water molecules with microwaves, that kind of thing. Yes, the more microwaves, the more water molecules affected. Yeah.
Not the maximum kinetic energy of the electrons. This also doesn't make any sense to a classical physicist because
So of course it does if you're a classical physicist isn't one that you made up. So pick a real person in history and then ridicule him with this notion that he had a classical theory. Now obviously again there's stuff people didn't know 300 years ago. Obviously, Benjamin Franklin didn't know he was putting plus and minus in the wrong places. But, I mean, this is just bullshit to say, like I said, they actually fixed some sort of logical errors. There wasn't any logical errors. There was just an absence of evidence to draw conclusions. And that's all there was. They didn't solve the crime wrong. They just hadn't solved it. And now you're showing up and you're saying I solved it, and you have the wrong answer because you're ignoring half the evidence on the table.
Let's see. If we increase the intensity, then we'll be increasing the amplitude, so we'll be more likely to free electrons, and they'll be coming out faster as well. But the quantum physicist says...
Right, so why would they think they would come out faster the more I throw in there? Right, why would I think if I throw 90-mile-an-hour baseballs at glass vases, why would I think the glass is going to fly off faster because I threw more baseballs? Right, so I'm breaking vases with baseballs. Why would I think because I'm breaking more vases, the glass is going to fly off faster? I wouldn't think that. So again, this is just such a despicable tactic to pretend you fixed some problem. No, nobody had that problem. Nobody was thinking the glass flies further because, or the punch is harder because I have 10 guys punch one guy, that somehow each punch is harder. No, there's just more of them.
No, you've got that wrong. You need to understand that if I'm increasing the intensity, I'm simply sending more photons in. And so I will get more electrons out. but they will all be going the same maximum speed. I'm saying K max because there could be some other things going on. They might be going weird directions, or there might be some weird absorption or something. But there's a final awesome thing that comes from this photoelectric effect. So both of these say quantum is real and shove it, essentially. But let's get a little more space over here. And I want to say that you can make a graph now. I love graphs. I'm going to make a graph of, well, it's going to be frequency on the x-axis, and it's going to be the maximum kinetic energy, which, remember, we're measuring by the stopping potential. These super stubborn electrons are going to go the wrong way because they're kicked out of...
So he's just going to draw a line starting a little bit down the line, and then it goes up. You know, it's not going to be that exciting. Trust me.
Their emitter with so much kinetic energy that they do actually manage to go uphill, energetically speaking, and cause a current even when there's a stopping potential on. So we can measure the maximum kinetic energy. And the cool thing is, the brighter the frequency, these electrons do come out with a higher... Did I say that right? What I mean is...
Yeah, the brighter the frequency. Yeah, you didn't say that quite right.
The higher the frequency, they come out with more kinetic energy. So you make a little graph right here, and you're thinking, well, if I use a sodium...
So the argument would be that's like, all right, if we used it as a strictly, if we use just a pendulum analogy, you can sort of understand that when I first hit the pendulum, it starts to slow down. So its initial velocity is its fastest velocity, and all the other velocities it's going slower and slower and slower until it stops. So the longer I wait to hit it again, the less energy it has. And so whatever I'm adding is only going to be added to the energy it already has in that direction. So if I hit it really soon, you know, right after I hit it the first time and I hit it again, then I'll have the maximum amount of energy I can possibly put into the pendulum. I'll get the maximum amount of distance out of it in terms of how much gravity it can overcome. But the longer I let gravity work on it, and the argument would be the longer I let the atoms dissipate the energy of the initial bit that hit, the less likely I am to add more velocity. The velocity I'm adding is going to be added to a lesser and a lesser and a lesser velocity. So the sooner I hit the second time, the more likely it is, the more energy I'm going to be getting as a total amount of energy in the system. The longer I wait, the more likely the energy degraded.
Check this out. If I use a sodium piece of metal in my tube, and that would be okay. Sodium's not very good if you're in air, but I mean, you could keep it clean in a vacuum, right? If you use a sodium piece of metal, you might get this pattern right here. You get some data and you find, whoa, if I increase the frequency, then I'm getting more and more energetic electrons spit out. Of course, if I get to this...
So that's why it just has something to do with how the atoms are transmitting, you know, how the atoms are transmitting the electron. So it's almost like how the electricity, so to speak, is moving. The electron's moving is electricity. How fast it moves through the material, the substance, is essentially going to dictate, you know, at what point it triggers in terms of going fast enough to eject electrons, and well, that would also be the binding strength of the material, right? So that's the second thing, is how hard are the electrons attached, and that's going to be something else you have to fight. That's just saying you're adding more gravity to the system, pushing the pendulum. So obviously it's going to be, you're going to need to hit it sooner to get the pendulum up to a certain height, because you have more gravity to overcome.
Point right here, this I'm going to define as the threshold frequency, because at that point I'm getting maximum kinetic energy of 0. I'm not getting any electrons out right here. So then you'd find that to be the case. And if I take a different metal, let's say that I take a metal like gold or something and I make it out of gold, I get a very, very similar pattern right here, but it's got a different, what are you going to say? It's got a different x-intercept, which is f naught for gold. And I mean, we could look at this equation right here. This is a very interesting equation. But with this threshold,
it's a wrong equation. It really is just really wrong-headed to think that it's just about frequency when it's really H could be against polarization. They could just change this F and they wouldn't hurt anything and just say polarization. So H times polarization equals energy. It also worked because polarization is proportional to frequency. So, so there's lots of ways you can understand this. But it also has to be understood that it isn't anything called its total or real energy. The energy in this equation just has to do with the phenomenon of freeing electrons. It doesn't have to do with the phenomenon of just moving electrons. So the duller light moves electrons maybe more distance total. The total distance the red light's moving the electrons is more total distance than the blue light. But the point is you hit the pendulum in the right way, right? The red light can do lots of swinging of pendulums. It just doesn't swing them as high.
Frequency, and we must mean something very different. I guess what I'm saying, let me define threshold frequency here. Threshold frequency is defined as, well, they call this energy, the threshold energy, they call it the work function. That's the energy that it takes to get the electron from here to here, and they use the letter 5 for it. I don't really know why, but I'm just...
Yeah, well, since it's not a real thing, because it's going to change for every single atom and every single circumstance, so it's not a real thing.
Doing algebra on this guy right here, so I'm saying F is phi divided by H. So this defines what's called the work.
So this gets even more messy now, because now they're going to change what a frequency is. When we know what a frequency is, it has a standard measured value, and so why would you mess with the frequency?
Function. And you should think of the work function as the amount of energy required to bail your uncle out of jail. If the work function of energy is given to your uncle, then your uncle will be free. Now, if you give your uncle more money than the amount of money required to get him out of jail, then he will leave jail with some money. There's no problem with that, giving your uncle a little bit extra spending money. Maybe he needs to get some new pants. I don't...
Yeah, but it's not that simple. It's not that linear, I don't think. So I don't think they can ever demonstrate that it's exactly the extra amount of energy that you put in all of it will be realized in the velocity of the electron, because you don't know what it's actually doing to the other atoms. So some of it might be dissipated in the material. So they don't have any proof that all of it ends up. They just have a vague idea that, yeah, well, it's going to make it go faster, but they don't have any proof that all of it goes into spending money.
No, orange looks good on him, but not...
I mean, you might have had to spend some of the money bailing your uncle out. You might have had to, get somebody out of bed, get the lawyer there, give them $20, blah, blah, blah.
That good, and he doesn't want to wear what he came in with. So, work function is... What I'm trying to say is work function is the minimum amount of energy your uncle needs. If you give him more energy, that is, you give him a higher frequency photon, then he will leave with more energy than, he will leave with some energy, some leftover energy. And I guess this is something to do with this energy right here. We could get an equation that acts like that. And I'm going to say...
So again, going back to my argument, that this, yes, the sooner you hit, the more, like I said, the less you've lost. So the longer you wait to hit it again, the less potential you have to move it up higher. So well, I already did it. I already explained it. The pendulum argument.
That the maximum kinetic energy, watch this, K max is, well, it's the energy of the photon minus the work function. Our book actually uses a W naught, and I have never seen that anywhere else, so I'm not going to use it. I'm going to use the standard 5. The maximum kinetic energy of an emitted electron is the energy of the photon that came in minus the work function of the metal. And the
Right, and again, this is just a formalization of the variables, but we don't necessarily know all the variables. Like I said, hitting it that second time, you probably are dissipating some energy in other directions. Just like the initial drop dissipates energy over a large area, you're probably going to dissipate some of the energy of the second drop that you're hitting behind the guy. All of the energy won't go to him. Some high percentage of it will, maybe 40% or 30%. But you might be losing a lot of the energy in other directions also, and so they don't have any explicit evidence of this, that this formula is complete. That saying work function includes all the administrative costs. It just doesn't.
work function of the metal isn't on this graph, but if I'm thinking about this graph in terms of y equals mx plus b, I want you to tell me where I can find the work function. I need you to look at this as if you just made this graph and that graph. And remember, these graphs are actually stopping right here. There is nothing going on below that. But
the work function is just the slope of the line, so it doesn't mean much.
I want you to find phi, the work function. Good luck. Please remember that this is a big part of understanding modern physics and why quantum mechanics.
Right, so this really mushy stuff, barely connected analogies, blah 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 blah, is what they call good physics. And yeah, we know what we're talking about. These are the right answers. That's why I'm going to just tell you this is the way it is. And it's a lousy description.
Was necessary. Do some problems, please, because you'll find the units of maximum kinetic energy are generally given in electron volts. If the units are electron volts, then I suppose, look at that, isn't that cool? One electron has an electron volt of 1 if it goes through 1 volt potential. So we can talk about its energy in terms of 1 electron volt if it manages to escape a 1 volt stopping potential. That's a really handy unit for the maximum kinetic energy. You could put it in electron volts right there. And that's probably how problems will be written for you.
Right, but it's only handy if you understand that it takes 468 million electron volts to snap your fingers. You know, but whatever.
You should be practicing those. Stop watching videos. Do some problems.
Oh no, think about what they're saying and think about, well, what evidence did they use to draw that silly conclusion? Yeah, that's what you should be doing.
Sorry, one final thing on that graph.
Yeah, slope, so I was right. It's time for this, I think. Yeah. Cool.
Made graphs of kinetic energy maximum versus frequency, and they went like that. What's the slope here? Get it?
So I guess he was giving people the answer. Anyway, so I guess that's it. The end and such. Alright, so I feel we've done enough. I can do some of this. Yay. Oh, I like the blue. Yeah, we'll go with that. And then if I bring back Firefox, it puts me back in the other window. Anyway, it doesn't really matter. Alright, so, yeah, we'll call it a video. Nothing much to report on. Now, just have to wait and see if we can provoke some kind of challenge. You know, $1,700, Doc Schroeder. $1,700 to play my 15-minute video, you know, on the subject of photons, and yeah, see if we can get, so you know, but no, can't. Anyway, I mean, it's clear. I mean, I've made the argument. Their theory is cooked. Okay, the wave notion of a photon is just cooked. It's dead. It doesn't work. It hasn't worked for hundreds of years. It's always been just a big fraud and a fake, in the sense they just fudged all the inaccuracies and fudged their way around them by talking about infinitesimal slits and infinitesimal impediments and all of that mush, because that's the only way they could get their logic to match. They couldn't make it logically work unless they terribly cheated the experiment. Did it upside down and back assward and sideways. They had to do the experiment in some silly way to make their theory reasonable. And it wasn't reasonable to do that, but they didn't tell anybody that's what they were doing. They didn't tell anybody that, we're, creating conditions that are going to create a very irregular effect. And it's the irregular effect is good for us. Gives us hope. But the regular effect, that isn't good for us. Single slit, let's not talk about it too much because it's not good for us. Anyway, I've been over it already. So, till the next time and such, this should work.